I'm honored to be back at APEC to present on this exciting subject. This is going to be dense, and I've got a lot of material to cover. So just buckle up and here we go. I have some very exciting things to share with you today. More and more people are no longer content with the status quo of QED. There's a change in the wind, and we're watching this change happen right before our very eyes in real time. And I'm on slide 1, correct? Yes. We're here to perform a forensic autopsy on modern physics and a resurrection of mechanical engineering. For 100 years, humanity has been trapped in a mathematical hall of mirrors called QED, quantum electrodynamics. But today, we're going back to the foundational fracture of 1924 to show you how we missed the most powerful engine in the universe, the vacuum itself. We will show you how physics traded a real physical continuum for a series of mathematical ghosts. I start with the premise that all matter and energy are emergent properties of ZPE field density. What if we could change ZPE density locally? Now let's go back to the foundational fracture of 1924 to 1927. In 1911, Max Planck published his second theory. He didn't just suggest a vacuum had energy, he postulated a real physical zero-point energy that existed at absolute zero. But between 1924 and 1927, 4 consecutive papers effectively ghosted this vacuum energy. 1, in 1924, Louis de Broglie suggested particles could be waves, but he left the medium out of the equation. 2, in 1925, Born, Heisenberg, and Jordan developed matrix mechanics, the first form of QED. It wasn't about the mechanics of the vacuum. It was about the math of the measurement. Number 3, 1926, Erwin Schrödinger gave us the wave equation. He visualized the hydrogen atom as a wave system, but again, the ocean those waves moved through was ignored. And in 1927, Heisenberg's uncertainty principle was the final blow. It institutionalized the idea that because we couldn't measure the ZPF specific jitter, we should treat the vacuum as a mathematical construct, a placeholder of probability rather than a physical plenum. For the rest of this presentation, when I say jitter, I mean the German word that I cannot pronounce. I'm not even going to try to do that again. Despite Planck's second paper in 1911, postulating a real ZPE, these 4 papers turned the course of physics away from the classical approach and toward what is known as QED. This approach treats the ZPE as a hypothetical and only useful as a mathematical construct. At this point, I'm going to put a pin in the historical prelude and come back to it in a few minutes. Right off the bat, I want to address some serious misconceptions about the ZPE that I noticed after my last APEC presentation back in October. What the ZPE is. It's homogeneous and isotropic sea of stochastically fluctuating waves of all wavelengths down to the Planck cutoff length. They're non-propagation waves similar to ocean waves, or you could even think of cymatics, where the ZPE waves are stochastic superpositions of modes like resonant vibrations on the plate of the vacuum. They are Lorentz-invariant. There are many more short wavelengths than long ones due to its frequency cubed spectrum. Double the frequency, example 1 Hertz to 2 Hertz, energy density jumps 8x. At 4 Hertz, it jumps 64x, and at 8 Hertz, 512x, and so on. Lorentz invariance for the ZPE waves has 3 consequences. 1, it means the velocities through the ZPE cannot be detected. Second, it means that the ZPE is made up of many more short wavelengths than long ones. And third, because the enormous turbulence of the atomic and subatomic scales, particles get jittered by the impacting waves of the ZPE constantly, giving rise to their quantum uncertainty in their position and momentum. Planck's constant, h bar, is a measure of this quantum uncertainty, and this uncertainty is dependent on the strength of the ZPE. This is another reason why Planck's constant is a measure of the strength of the ZPE according to SED physics. Another intrinsic property of the ZPE are its associated particle-antiparticle pairs. In QED, they're called virtual particles because they only exist as a mathematical construct. The caveat to that is that the theory suggests that upon reaching the energy level of the Schwinger limit, these virtual particles suddenly become real. In SED physics, they are not virtual because they're always real in relationship to the frequency cubed spectrum of the ZPE. Because ZPE waves are of all wavelengths moving in all directions simultaneously, dipoles of these waves will interfere constructively, temporarily forming very real particle-antiparticle pairs. In any instant, there are more than 10 to the 63rd such particle pairs in any cubic meter of space. This has several implications. One, because these particles are electrically charged, they control the electric properties of the vacuum known as permittivity. And because these charged particles also move, and a charge in motion, an electric current, always produces a circling magnetic field, they also control the magnetic field properties of the vacuum known as permeability. Because the strength of the ZPE, the number of ZPE waves per unit volume, controls the number of particle-antiparticle pairs in a given volume of space, any change in the strength of the ZPE changes the number of particle-antiparticle pairs per unit volume. Now think about that. You think that might have anything to do with the Biefeld-Brown effect or Ferris-Williams dynamic theory unifying gravity and electromagnetism? I think it might. 2, because for their very brief existence, the particle-antiparticle pairs are very real, just like all other particles, they too get jittered by the impacting ZPE waves. Pairs are jittered at the constant frequency. This creates secondary radiation. 3, they can and do absorb light. 4, pairs enhance ZPF Lorentz drag on accelerating charges. Implication, inertia emerges as vacuum resistance. And 5, Barry Setterfield suggests the secondary radiation of particle-antiparticle pairs being jittered polarizes the vacuum, meaning net attraction toward areas of more virtual particle pairs, large mass objects. And this is the mechanism of what we know as gravity and why it's so weak. What SED is or what SED and the ZP is not, rather. Even though SED physics has been around since the 1960s and made somewhat popular by Heischrud and Puthoff in the 80s and 90s, it still remains that QED is the mainstream physics. Because SED physics has continued to be marginalized in 2026, SED is not an idea familiar to many people. Whether people have heard of it or not, they've been left with an unclear understanding of what it is. Some people try to describe it as QED with a little zero-point energy mixed in. Even a basic understanding of these things that I've laid out would dissuade this incorrect understanding. The 4 papers of the 1920s that led to QED's physics all came about as an attempt to explain Planck's first paper without a real ZPE. It stands to reason, then, that one cannot simply mix a real ZPE into the physics that doesn't acknowledge it as a real entity in the first place. Also, it is not the classical ether. Modern critics often conflate the ZPE with the 19th century luminiferous ether. This was the concept of a fixed mechanical Newtonian medium for light propagation. The classical expectation was that an absolute velocity through the ether could be determined. If the ether behaved like a static solid, then as Earth moves through it, we should be able to detect an orbital wind, since Earth's orbital velocity is 30 kilometers a second. It should produce a large fringe shift. Going back to the Michelson-Morley experiment we just talked about. A fringe shift was observed, but it was far smaller than predicted, corresponding to roughly 8 kilometers a second rather than 30. Textbooks call the Michelson-Morley experiment a null result, but the raw data showed a persistent small shift. Mainstream science ignored this because it was within the margin of error. Barry Setterfield, in chapter 7 of his book, Cosmology and Zero-Point Energy, recognizes it as partial entrainment. Even though an absolute velocity through the ether was not proven, the small fringe shift did prove something. Near large masses like Earth, the ZPF density is not uniform. The Earth entrains the ZPF. This has a refractive index connection. Setterfield notes that in the entrainment, this entrainment effectively changes the refractive index of space near the planets. The small 8 kilometers a second shift measured by Michelson and Morley wasn't an error. It was a measurement of partial entrainment and revealed that the vacuum is not in an empty void, but a physical frequency cubed spectrum and Lorentz-invariant, whose density is locally coupled to Earth's gravitational potential. It was the first unintentional measurement of a ZPF gradient. Summing up, you should now be thoroughly equipped with a basic understanding that SED is not QED with a little ZPE mixed in, and nor is it the classical luminiferous ether either. Now, big news this week. Something else needs to be mentioned here. And it's so new, I don't even have a slide for it. It comes about because of the Eric W. Davis and Eric Weinstein debate. Weinstein used a term I've never heard of before, and Eric Davis didn't seem too familiar with it either, EED. So what is EED? Well, I did some research. There's a lot of confusion right now because EED is not a single universally accepted theory the way QED and SED are. In current discussions, EED usually means extended electrodynamics or sometimes emergent electrodynamics. Different groups use the acronym for slightly different frameworks. It came about more recently in the 1990s to 2000s, and the idea is that electromagnetism itself might emerge from deeper vacuum structures. Examples appear in condensed matter analog models and topological field theories. It's suddenly popping up because, one, there's a lot of interest in vacuum engineering, two, the UAP advanced propulsion discussions going on, and three, gauge theory debates. Even though SED and EED started differently, they both imply the same deeper concept. Vacuum behaves like a physical medium. I don't like the word medium. Let's use plenum. Because of recent experiments, including the dynamic Casimir experiments, metamaterials that can reshape electromagnetic vacuum modes, and nanoscale resonators, vacuum engineering is starting to feel less philosophical and more practical. More physicists are becoming comfortable with the idea that physical constants and forces may emerge from interactions with vacuum fields. Fix the screen there. Both SED and emergent electrodynamics ultimately point toward a similar physical picture. The vacuum behaves like an electromagnetic ground state medium. Particles, inertia, and fields emerge from interactions with that medium. The biggest physics debate quietly forming right now is not QED versus SED versus EED. It's whether the vacuum behaves more like a quantum field or like a condensed matter medium or quantum fluid. Interestingly, this ties directly into another recent mic drop moment this week. Sonny White's paper, Emergent Quantization from a Dynamic Vacuum, published March 9th, 2026 in Physical Review Research. This paper explicitly assumes the vacuum behaves like a condensed matter medium or quantum fluid and shows that the quantum mechanics can emerge from it. That is to say, quantization is a resonance property of a dispersive medium. A lot going on this week. Now, let me get back to the historical prelude. Paul Dirac, 1902 to 1984. Dirac's work was central to the development of QED, the Dirac ghost in the ontological void. In 1928, Dirac formulated his equation, merging quantum mechanics with special relativity. He predicted the positron, the first antiparticle. But to save his math from negative energy states, he had to invent the Dirac sea, an infinite ocean of electrons filling the vacuum. Dirac gave us the virtual particle pair. In QED, these pairs are ghosts, mathematical artifacts that pop in and out of nothingness. Because these ghosts create infinite energy results, physics invented renormalization, a fancy word for subtracting the infinity to make the numbers match reality. This created an ontological void, a physics that is incredibly predictive, but offers zero explanation for why the vacuum behaves as it does. Dirac's relativistic quantum mechanics and field quantization helped establish the dominant quantum field theoretic paradigm QED, which pushed classical alternatives like SED to the fringes. In short, Dirac's work was a cornerstone of the quantum revolution that elevated QED and marginalized the classic stochastic approaches like SED. At 0 Point Field Technologies, which is my company, we're paying off the Dirac debt and filling the ontological void with the science of the real ZPE, with stochastic electrodynamics. The reality of the plenum. In SED is derived by key figures that we're about to explore. Virtual particle pairs are always real. They are the wave crest of the dipoles of the ZPEC. Matter does not pop out of nothing. It is a standing wave within the plenum. And once you realize a vacuum is a physical continuum, you realize you can apply hydrodynamics to it. More on this in a minute. Stochastic electrodynamics developed in the 1950s through the 70s by Timothy Boyer, Trevor W. Marshall, and De La Pena, and popularized later by Aish, Ruda, and Puthoff in the 80s and 90s, is a classical alternative that attempts to explain quantum effects through real 0 point field fluctuations. Key figures and how their work challenges Dirac's framework and supports SED as a viable alternative. Timothy Boyer, 1941 to present. Boyer is the primary architect of modern SED. In a series of papers in 1968 to 1975, he demonstrated that classical electrodynamics plus a real isotropic Lorentz-invariant zero-point field reproduces several core quantum results: Casimir force, Lamb shift, black body spectrum, van der Waals forces, key point versus Dirac. Boyer showed that the zero-point field's frequency cube spectrum provides the physical mechanism for the quantum fluctuations that Dirac's relativistic quantum mechanics treated as operator-valued fields requiring renormalization. Next, Trevor W. Marshall, 1947 to present. Marshall collaborated closely with Boyer. His work emphasized the stochastic nature of the ZPE and derived the Planck spectrum from classical SED, the origin of the Heisenberg uncertainty principle as arising from real ZPE fluctuations, not fundamental indeterminacy. Marshall's derivations directly counter Dirac's second quantization. The vacuum does not need creation annihilation operators, and real random EM waves suffice. Third, Louis de la Peña, 1931 to present, and Ana Maria Seto, 1946 to present. They developed a rigorous stochastic electrodynamics variant. Their books and papers, especially the quantum dice from 1996, show that quantum mechanics can be derived as the statistical mechanics of particles immersed in the real ZPE field, and a Schrodinger equation emerges from the Langevin equation with ZPE driving terms. They argue that Dirac's whole theory and negative energy solutions are unnecessary artifacts once the ZPE is treated as a real physical field. While I was putting together this presentation, I was curious if any of these people had any recent workout, and I found Ana Maria Seto's X account not very used at all, not many followers, not many posts. One of the most recent posts I found was from September of last year, and it had an article that is extremely relevant to this conversation. And so I'm going to read part of that article right now. It was posted in Physics World, September of 2025, called Quantum Foundations Toward a Coherent View of Physical Reality. 100 years after its birth, quantum mechanics remains one of the most powerful and successful theories in all of science. From quantum computing to precision sensors, its technological impact is undeniable, and one reason why 2025 is being celebrated as the International Year of Quantum Science and Technology. I agree with this. It's just that, in my opinion, SED could have done the same thing. Yet, as we celebrate these achievements, we should still reflect on what quantum mechanics reveals about the world itself. What, for example, does the formalism actually tell us about the nature of reality? Do quantum systems have definite properties before we measure them? Do our observations create reality or merely reveal it? These are not just abstract philosophical questions. Having a clear understanding of what quantum theory is all about is essential to its long-term coherence and its capacity to integrate with the rest of physics. Unfortunately, there is no scientific consensus on these issues, which continue to provoke debate in the research community. That uncertainty was underlined by a recent global survey of physicists about quantum foundational issues conducted by Nature 643-1157. It revealed a persistent tension between realist views, which seek an objective, visualizable account of quantum phenomenon, and epistemic views that regard the formalism as merely a tool for organizing our knowledge and predicting measurement outcomes. Only 5% of the 1,100 people who responded to the Nature survey expressed full confidence in the Copenhagen interpretation, which is still prevalent in textbooks and laboratories. Further divisions were revealed over whether the wave function is a physical entity, a mere calculation device, or a subjective reflection of belief. The lack of agreement on such a central feature underscores the theoretical fragility underlying quantum mechanics. More broadly, 75% of the respondents believed that quantum theory will eventually be replaced, at least partially, by a more complete framework. Encouragingly, 85% agree that attempts to interpret the theory in intuitive or physical terms are valuable. This willingness to explore alternatives reflects the intellectual vitality of the field, but also underscores the inadequacy of current approaches. Beyond interpretation, we believe that this interpretive proliferation stems from a deeper problem, which is that quantum mechanics lacks a well-defined physical foundation. It describes the statistical outcomes of measurements, but does not explain the mechanisms behind them. The concept of causality has been largely abandoned in favor of operational prescriptions, such that quantum theory works impressively in practice, but remains conceptually opaque. In our view, this is Ana Maria Seto and Louis de la Peña, the way forward is not to multiply interpretations or continue debating them, but to pursue a deeper physical understanding of quantum phenomenon. One promising path is stochastic electrodynamics. a classical theory augmented by a random electromagnetic background field. The real vacuum or zero-point field discovered by Max Planck as early as 1911. This framework restores causality and locality by explaining quantum behavior as the statistical response of particles to this omnipresent background field. Over the years, several researchers from different lines of thought have contributed to SED. Since our early days with Trevor Marshall, Timothy Boyer, and others, we've refined the theory to the point that it can now account for the emergence of features that are considered building blocks of quantum formalism, such as the basic commutator and Heisenberg inequalities. Particles acquire wave-like properties not by intrinsic duality, but as a consequence of their interaction with the vacuum field. Quantum fluctuations, interference patterns, and entanglement emerge from this interaction, without the need to resort to non-local influences or observer-dependent realities. The SED approach is not merely mechanical, but rather electrodynamic. Thank you, Ana Maria Seto and Luis de la Peña, for that amazing articulation from September 2025. I mean, geez, he's 95 now, and she's 80, and still so passionate about the subject. Amazing. On to Louis de Broglie, 1892 to 1987. He was a French physicist who won the 1929 Nobel Prize for his 1924 doctoral thesis on the wave nature of matter. In 1927, he proposed a deterministic pilot wave interpretation, later revived by Bohm in 1952. Particles follow definite paths guided by real waves, classical-like reality that directly challenges Dirac's 1928 abstract operator formalism and probabilistic wave functions and second quantized fields, which produce the infinities that QED must renormalize away. This aligns perfectly with stochastic electrodynamics. The real ZPE fluctuations cause the jitter that maintains atomic orbits and produces the de Broglie wavelength. Heischrud-Puthoff, in their Physics Review A49 678-694 from 1994, derived the relation directly from the ZPF Lorentz drag on charges, treating waves as physical electromagnetic modes of the actual ZPE, not Dirac's mathematical abstractions. In the 1950s and 60s, de Broglie publicly regretted his earlier support for the Copenhagen interpretation and revived causal deterministic mechanisms or mechanics with hidden variables. His Lambark 1962 book, New Perspectives in Physics, states that physics took a wrong turn in the 1920s. Next, Anthony L. Peratt, 1940 to present. He's a plasma physicist, worked both at Livermore and Los Alamos. Peratt is not a core SED theorist, but provides complementary plasma cosmology support. His work includes large-scale electromagnetic simulations with Z-pinch and plasma filament experiments that reproduce galactic morphology without dark matter, and demonstrates that electromagnetic forces dominate gravity and cosmic plasmas, aligning with SED's emphasis on real EM fluctuations. Countering Dirac and establishing SED, Dirac's 1928 equation and second quantization were brilliant, but introduced virtual particles as mathematical constructs only, negative energies, and infinities requiring renormalization. Boyer, Marshall, and de la Peña collectively showed that most quantum effects Dirac's framework explained can be reproduced classically by a real fluctuating ZPE field obeying Maxwell's equations plus stochastic driving. No need for renormalization, creation operators, or virtual particles as ontological entities. ZPE itself provides the physical fluctuations. Peratt's plasma simulations reinforce that EM forces, including ZPE scale fluctuations, can explain large-scale structures without invoking dark matter or purely gravitational models. SED is not mainstream because QED's predictive success has kept it dominant. But these researchers demonstrate that SED is a viable, parsimonious alternative that avoids QED's mathematical scaffolding while reproducing its results. They also share a common agreement that the Copenhagen interpretation of quantum mechanics may be incorrect. In short, Dirac built the quantum edifice. Boyer, Marshall, de la Peña showed a classical foundation was possible all along, and Peratt extends the argument to cosmology. HRP expounded on these ideas in their seminal 1994 paper, Inertia as a Zero-Point Field, Lorentz Force, Physics Review A49. HRP's work is the bridge that made SED a serious alternative interpretation. It shows quantum mechanics emerges from classical electrodynamics plus a real ZPF without Dirac's operator formalisms or infinities. Their later papers further argue the points. Barry Setterfield expands on HRP's ideas in several important ways on his website, barrysetterfield.org, and in his writings, specifically Cosmology and the Zero-Point Energy. I'm going to skip to point number 2 here, time-varying ZPE density. Unlike HRP, who treat ZPF field as fixed, Setterfield argues that the ZPE density has increased over cosmic time. In the early universe, lower ZPE density meant inertial drag was weaker, a higher primordial speed of light, a lower Planck's constant, longer atomic lifetimes, and faster atomic processes. As ZPE density rose, Planck's constant increased, C decreased, stabilizing atoms and slowing atomic processes. Emergent constants from ZPE density, Setterfield explicitly links HRP's mechanism to his variable constant model, where Planck's constant is proportional to ZPF density, which measures the graininess of the plenum, and speed of light is proportional to 1 over the square root of ZPF density, and also where inertia and atomic stability emerge from this change in density. I'm going to skip this one. You can go back and read this one if you have the slides. In short, Setterfield builds on HRP by making the ZPF density time-dependent and cosmologically evolving, turning a static inertia mechanism into a driver of cosmic history and emergent constants. On to the Madelung equation synopsis. Erwin Madelung from 1881 to 1972 was a German physicist and published in 1927 the Madelung equations, which reformulate the time-dependent Schrödinger equation into hydrodynamic form. Here you see on the slide the 2 coupled equations, continuity equation and the momentum equation. And why these are crucial is they show quantum mechanics can be derived as the motion of a compressible quantum field with an extra quantum pressure term, Q. That produces non-classical effects, such as tunneling, interference, and uncertainty. They bridge wave mechanics and fluid dynamics, enabling quantum hydrodynamics. In the Miller framework, which we're about to talk about, and SED, they are essential for treating the ZPF as a real compressible quantum fluid, whose density gradients drive polarization, nonlinear saturation, Lorentz force asymmetries, and thrust scaling. Madelung's insight makes the ZPF a tangible, manipulable continuum rather than an abstract mathematical construct. In the SED view, the Madelung equations become extremely useful because they let us treat the real physical ZPF as a compressible quantum fluid whose density gradients produce the quantum potential Q classically. No need for wave function collapse operators or renormalization. One last person to talk about in the historical prelude before moving on to the Miller framework. Ferris Edward Williams. We conclude our historical prelude with Ferris Williams, a brilliant American physicist and former researcher at Los Alamos National Laboratory, best known for his dynamic theory in the 80s, a 5D unification model for space-time in one compactified dimension. His work aims to reconcile gravity with electromagnetism. It treats gravity, electromagnetism, and quantum effects as emergent from this higher dimensional geometry. Williams hypothesized that altering the 5th dimension could manipulate inertia and energy, potentially enabling warp-like drives or fusion enhancements. Yes, now that's the kind of exciting physics we're talking about. However, I state unequivocally that Barry Setterfield's emergent constants in cosmology offers a superior path over Ferris Williams' 5D dynamic theory because it is more empirically grounded, physically intuitive, and consistent with observed data while avoiding the complexities of an extra dimension. Setterfield's model centers on the zero-point energy field's density as the driver of cosmic evolution. As ZPE density increases over time, Planck's constant rises, speed of light slows down, and other constants adjust proportionally with HC invariant to maintain atomic stability and the fine structure constant. This explains redshift anomalies, atomic decay rate changes, and cosmological fine-tuning through a real physical mechanism, the frequency cubed spectrum of ZPE waves, surging the plenum's graininess. It's deeply harmonious with SED and HRP's work, where inertia emerges from Lorentz drag from this real field. And Setterfield's approach is testable, backed by historical data on C measurements and decay rates without invoking unobservable dimensions. In contrast, Williams' 5D dynamic theory, while innovative for propulsion, anti-gravity, superluminal effects, it's more speculative, relying on abstract higher dimensional math without direct empirical anchors, similar to string theory's challenges, and it lacks Setterfield's ZPE-centric focus, making it less intuitive for vacuum engineering and less consistent with SED's real field fluctuations. But, and this is a big but, it's not far off. If you substitute the compactified 5D dimension for the very real frequency cube spectrum of the ZPE and his mass density x to the fourth acting as a proxy for the ZPE, you basically have very nearly the same thing. Both versions embrace variable constants to resolve cosmological puzzles, example fine-tuning and redshift, and counter QED's fixed vacuum and renormalizations. What it boils down to is that you don't need a fifth dimension, you just need an understanding of the frequency cube spectrum of the ZPE and its associated particle-antiparticle pairs, and what happens when you modulate ZPF density. Zero-point field technologies has made Setterfield's emergent constants and cosmology more engineering-oriented through the Miller framework, which codifies ZPE modulation into 6 pillars for practical applications, like our ZPF array, which is designed to be a first-of-its-kind, solid-state quantum hydrodynamic engine that pumps the local ZPE density gradients for quantum vacuum propulsion, directed Lorentz asymmetries, and vacuum-catalyzed aneutronic fusion applications. By integrating Setterfield's emergent constants with HRP's drag, we've transformed cosmological theory into metric engineering. This one, I'll let you read, and you can look back on that later in the slides. I'm going to skip ahead here. You can also go back and read this one. Now the bridge. Now we build the bridge to practical applications through the Miller framework, a paradigm for engineering the vacuum's emergent properties. We contrast QED's virtual constructs with SED's intrinsic particle-antiparticle pairs arising naturally from ZPE wave crests and dipoles, and address QED's extreme energy boundaries, such as the Schwinger limit, by introducing the recursive Miller saturation threshold as a more accessible onset mechanism for vacuum modulation. We will explore the 6 pillars of the Miller framework and demonstrate how SED enables tangible innovations in propulsion and fusion. We believe that our ZPF array will provide falsifiable predictions and tests that will position SED as the mainstream successor to QED by offering a unified, engineerable view of reality. From understanding the ZPF to engineering it, imagine the ZPF as an infinite ocean. Its waves crash stochastically, their superposition creating the subtle pressure gradients that jiggle particles and sustain atomic stability. But what if we could actively pump those waves, deliberately raising local ZPE density inside our cavities to engineer controlled pressure gradients and then direct that ocean like a symphony conductor to reshape reality? This is the essence of the Miller framework, developed at ZPF Technologies as an SED-based foundation for quantum metric engineering, drawing from Barry Setterfield's insights on emergent constants from ZPE density and HRP's model of physical Lorentz forces. The framework treats the vacuum as engineerable. This shift empowers innovations such as propellantless propulsion by creating directed ZPF asymmetries and vacuum-catalyzed aneutronic fusion by softening Coulomb barriers without extreme heat. Intrinsic particle-antiparticle pairs in SED. In QED, particle-antiparticle pairs are virtual mathematical placeholders in Feynman diagrams. They pop in and out as perturbative corrections require renormalization to cancel infinities and only become real at the extreme Schwinger limit. In SED, these pairs are intrinsic and physical. They emerge naturally from the real ZPE wave crest. Peaks create electrons, troughs create positrons, and driven by the frequency cube spectrum, they're always present as part of the plenum's stochastic jitter. No extreme threshold needed. Setterfield models show high-frequency modes provide persistent pair fluctuations while preserving vacuum isotropy. This shift from mathematical ghosts to real vacuum excitations is what lets us engineer the plenum instead of fighting it. HRP and reinforcement. HRP showed that the real ZPF's Lorentz forces on charges produce the same jitter that mimics the de Broglie wavelength and uncertainty principle, but entirely as classical physics. In SED, each ZPE mode carries energy Planck's constant frequency over 2 with pair creation, threshold 2 mass sub E c squared for the electron positron. The spectral density formula you see here supplies more than enough high frequency modes for persistent pair flux at all scales, no Schwinger limit required. The frequency cube dependence is the mathematical smoking gun. Energy density explodes with frequency, ensuring continuous real pair creation for constructive ZPE dipoles. No external lasers needed. This is real pair ontology, the foundation of vacuum engineering. Replacing the Schwinger limit with a recursive Miller saturation threshold. In the world of standard quantum electrodynamics, the Schwinger limit is treated as a rigid breaking point for space. It is mathematically defined as the moment energy density becomes so extreme that you've packed an electron's worth of rest mass energy into a tiny Compton volume. Mainstream QED treats these pairs as virtual bookkeeping, mathematical fluctuations that are forbidden from doing real work until an external force promotes them to reality at the Schwinger limit. This is a distinction without a difference for an engineer. In the Miller framework, we stop hedging. We recognize that the spectral density means the vacuum is already at that energetic threshold intrinsically. We don't need to promote these pairs from a mathematical ghost state. We're simply modulating a real pair flux that is already performing the work of maintaining the vacuum's impedance. Now, practically speaking, the type of energy referred to by QED to reach the Schwinger limit is electromagnetic energy, requiring either intense lasers, example petawatt facilities like ELI or NIF, compressing pulses to 10 to the 18th volts per meter, or specialized setup of extreme plasma fusion conditions. In contrast to the brute force electromagnetic approach of QED, the Miller framework emulates Schwinger-like effects by modulating the local ZPF density itself. As we increase this density, literally thickening the vacuum with additional wave modes, the particle-antiparticle pairs of the ZPE intensify their relativistic jitter at the Compton frequency. This jitter, already moving at velocities near c, escalates until these pairs back-react non-linearly on the ZPF. They begin scattering and absorbing waves, saturating the vacuum's response like a fluid reaching its viscosity limit. This is where the big reveal happens. Because Planck's constant is a direct measure of ZPE density, as we pump the density, Planck's constant increases locally. This trigger starts a recursive loop. 1, it increases the electron rest mass. 2, it expands the Compton volume. Consequently, the very definition of the Schwinger limit, the energy density required to break the vacuum, increases along with power. As we pour density into a unit of volume, the volume expands its capacity to hold more graininess without fracture. This gives it a recursive nature. Unlike the hard Schwinger limit of QED, which suggests space-time will shatter like glass, reaching its fracture point, our vacuum softens like dough. It yields to our kneading, enabling sustained effects like softened fusion barriers and metric gradients. By leveraging coherent ZPF resonance rather than stochastic brute force electric fields, we emulate the nonlinear polarization of the Schwinger limit at approximately 7 orders of magnitude lower potential gradient or field strength. We aren't just hitting the vacuum, we're harmonizing with its fundamental frequency to rewrite the local metric. Instead of fighting the vacuum to create a pair, we're using high frequency actuation to harmonize with the Compton frequency already present in the background. Because we're pumping a resonance, the energy required to reach a nonlinear state is exponentially lower, similar to how a singer breaks a glass with a specific frequency rather than a sledgehammer. For these reasons, in the Miller framework, the electron rest mass over the Compton volume is renamed the recursive Miller saturation threshold. This recursive softening isn't just theory for us, it's the operational basis for the 6 pillars of the Miller framework. The Miller framework codifies SED's principles in its 6 pillars for vacuum engineering, positioning ZPF Technologies as a leader in metric modulation. Pillar 1, the Miller-Madelung transition. A resonance-induced shift of the ZPF from isotropic stochasticity to anisotropic polarization. We treat the vacuum not as empty space, but as a quantum fluid governed by Madelung hydrodynamics. The mechanism. The spectral density formula you see here establishes the ZPF as a high-pressure plenum. By concentrating these high-frequency modes, the array induces Madelung pressure gradients. The result? Inertial forces and radiation reactions are recast as viscous back reactions, allowing us to guide Bohmian flows into a state of coherent asymmetry. Talk about that on pillar 3. By inducing these pressure gradients, we change the metric compliance of the local vacuum. In plain English, we're making space-time less rigid and more responsive to our pumping. We call this softening the metric, turning a stiff, unyielding void into a flexible, engineered vacuum. It's like a hydrofoil in a high-pressure stream. By modulating the density inside the cavities, we create a thick ZPF zone. The pressure difference between this engineered zone and the thinner ambient vacuum outside creates a suction effect, a net Lorentz force that pulls the lattice forward. We aren't throwing propellant out the back. We're engineering a pressure drop in the fabric of the plenum itself. Here you can see the formula. The formula in plain English says that the state of the vacuum is equal to the density of its energy multiplied by its phase or its internal rhythm. The continuity equation there tells us the vacuum follows the law of conservation of mass. It simply says the change in vacuum density over time plus the flow of that density must equal 0. In other words, the vacuum is a real fluid that can't be created or destroyed. It can only be thickened, thinned, concentrated, and skewed. When our array creates a surge, the fluid of space has to react. The momentum equation there, too, is the Navier-Stokes equivalent for the vacuum plenum, Newton's second law applied to a quantum fluid. It tells us that the fluid of space doesn't just sit there, it accelerates. Basically, the vacuum fluid accelerates under 2 influences, the classical potential and the quantum potential Q. Classical potential, V, is standard external forces. Quantum potential Q is engineered internal vacuum pressure. This is where it becomes revolutionary. Look at how we defined quantum potential. Notice it scales with the square of the Planck constant. Because we're surging the local Planck constant, the metronome of the vacuum, we're not making a small adjustment due to the square dependence. We're leveraging an amplified pressure gradient. We're turning a whisper into a shock wave to drive the array. Implications: it enables directed vacuum stress for propulsion. Our device is designed to induce this transition via proprietary means. As you recall, earlier we mentioned Sonny White's paper, Emergent Quantization from a Dynamic Vacuum. This work provides the external bedrock for Pillar 1. White uses the exact same Madelung equations we do, treating the vacuum as a compressible quantum fluid whose density gradients produce physical structure. The shift is profound. White's paper effectively replaces the mathematical ghost of the vacuum of QED with a real dispersive medium. This means we can engineer the 0-point energy and create quantum wake thrust while fully respecting the conservation of momentum. Our framework rests on 3 pillars of White's validation. 1, quantization is emergent. Quantum effects result from a dispersive vacuum medium, not abstract operators. 2, fluid dynamics. We're applying standard Madelung hydrodynamics to that medium. 3, geometric engineering. Our asymmetric cavities provide the constitutive profiles required to trigger these emergent forces at scale. White's paper confirms what we are banking on for our ZPF array. The vacuum is a reactive, compressible, and highly engineerable plenum. Pillar 2 is the Miller constant, or the refractive index. In optics, the refractive index describes how light bends in glass or water. We're applying that same logic to the vacuum metric. By increasing the vacuum susceptibility, K sub m, we're effectively thickening the plenum. Think of it this way. It's much easier to row a boat in water than it is in air, because the water provides the necessary resistance to the oar. We're transforming the air of the vacuum into water, giving the array the traction required to couple with the plenum. We aren't looking for propellant, we're looking for impedance matching. Here's the formula. Mathematically, this traction is a direct result of the resonance with our cavities. As we pump the system, the local ZPF density surges, which proportionally reduces the effective speed of light inside the array. We aren't breaking the laws of physics, we're reauthoring the local environment in which those laws operate to maximize energy transfer. If you increase Planck's constant, speed of light has to decrease. The HRP connection, this leads to a radical application of HRP, definition of inertia. If inertia is fundamentally ZPF drag, then by modulating local vacuum density, we can modulate inertia itself. We aren't just sending a signal into the void. We're turning the vacuum into an active coupling medium. We're impedance matching the hardware to the quantum vacuum, allowing for high efficiency transfer of engineered momentum. So what? Well, it's the refractive index, K sub m, is our force multiplier. It determines our leverage over the plenum. By engineering a higher K sub m, we achieve metric softening, reducing the vacuum's inherent resistance to change. This is the exact mechanism required to soften the Coulomb barrier for fusion. We're making the vacuum more compliant, literally making it easier for matter to move and interact within our localized field. Pillar 3 is the Miller-Bohm propulsion, or the trajectories. Directed momentum extraction via Bohmian trajectories in a polarized ZPF using Lorentz force asymmetries. This is how we convert the thickened vacuum fluid into directed thrust. It's like a hydrofoil in a high-pressure stream. The modulation creates the invisible rails that the array glides on. Inertial force ties directly to HRP framework. Acceleration distorts the ZPF spectrum, producing a back reaction, and the array's cavities asymmetries induce Lorentz imbalances, refracting stochastic flux into directed Bohmian paths. Implications: this unifies pillar 1 and pillar 2 into propellantless thrust. Through proprietary signal modulation, Bohmian trajectories are formed, effectively invisible rails within the vacuum fluid. This allows chaotic vacuum pressure to be rectified and directionally controlled. The core relation formula you see here, we return to the core physics of HRP. The effective inertial force is proportional to local vacuum density times acceleration. Inertia itself is vacuum drag. Formula is inertial force is proportional to minus ZPF density times acceleration. The minus sign is crucial. It tells us the vacuum is always pushing back against acceleration, exactly like viscous drag in a fluid. That opposing force is the drag we experience as inertia. Don't be confused, though. The minus sign does not mean negative ZPF density in this case. Now, usually this drag is symmetrical, but we have taken control of both variables. Through pillar 2, we engineer the density rho, and through our resonant frequency, we dictate acceleration alpha of the vacuum jitter. Our array's asymmetry then creates a Lorentz imbalance, refracting that chaotic energy into directed Bohmian trajectories. Think of the formula as the viscosity equation for the vacuum. Under ordinary conditions, the vacuum appears transparent. We move through it without noticing any resistance. But within the HRP framework, acceleration through the vacuum produces a reaction force proportional to ZPF density and alpha acceleration. That reaction manifests as a drag-like effect we interpret as inertia. The suction wake radiation reaction. What we're doing with the Miller framework is taking control of the ZPF density and alpha acceleration variables. By concentrating the ZPF density inside the cavities, we locally increase the effective viscosity of the vacuum. This enables the creation of a controlled gradient. Through our resonant frequency, we dictate the acceleration of the vacuum fluctuations. But the real magic is in the geometry. By using asymmetric cavities, we ensure that this acceleration isn't random. We're polarizing the alpha variable. We're forcing the vacuum to jitter in a way that creates a net pressure drop, a suction wake that pulls the lattice forward. We're controlling the density of the medium and the frequency of its reaction. By engineering this pressure gradient, we're rectifying the stochastic pressure in a single controllable direction. Visually, this would look like a vortex. Here's the array-specific expression. Looking at our array-specific expression here, you'll see that the force we generate is a direct function of the efficiency eta of our coupling and the square root of the energy inside the resonator. What this means for the hardware: eta ZPF is our proprietary coupling coefficient, how well our lattice grips the fluid, and the square root of gamma ZPF times E, the force scales with the energy density inside the cavity. The square root indicates a nonlinear resonant gain. And the local speed of light as we thicken the vacuum and the refractive index increases, speed of light drops, and the resulting force increases. This is our mechanical advantage. To wrap up pillar 3, 1, the formula tells us that any acceleration through the real ZPF produces a drag force proportional to local ZPF density. 2, in an isotropic undisturbed vacuum, this drag is perfectly symmetrical. It just resists motion in every direction equally. 3, our cavities plus resonance break that symmetry. They create a directional density gradient, higher ZPF density behind and lower ahead. And 4, that gradient turns the isotropic drag into a directed pressure field. In the Madelung hydrodynamic picture, any pressure field automatically guides the flow of the quantum fluid along defined paths. Those paths are the Bohmian trajectories, the invisible rails, visualized as a vortex. Pillar 4, the thrust scaling law, the definition, the quantum rocket equation. In traditional aerospace, we're governed by the rocket equation, which says your thrust is limited to how much stuff you can throw out the back. Consider this a quantum rocket equation, but there's one massive difference. Our fuel is the vacuum-plenum itself. We aren't trying to carry it with us. We're using it as we go, much like an airfoil uses the atmosphere or a propeller uses the ocean. The formula, the power of omega cubed. Look at the core formula. As we established in Pillar 1, the ZPF spectral density follows a frequency cube law. This is the secret to our scaling. As our signals are upconverted into higher frequency modes within the cavities, the energy density does not merely increase, it surges. This feeds back into the Miller constant. Mathematically, this produces a scaling factor of k sub m to the power of 1.5. The recursive snowball, the nonlinear surge. This creates a quantum snowball effect. Because the thrust scales nonlinearly with the vacuum density and our array increases the density as it operates, we get a recursive amplification. In plain English, the harder the lattice engine works, the thicker the vacuum becomes, and the more thrust we see. It's a self-reinforcing loop where the vacuum actually becomes more responsive the more you drive it. The implication, approaching saturation. The implication for APEC and for the future of propulsion is profound. We aren't looking at linear gains. We're looking at a system where thrust accelerates non-linearly as we approach the saturation threshold of the vacuum. We have moved beyond nudging the vacuum. We have found the mathematical and engineering key to leveraging the plenum for high-efficiency propellantless bursts. This is how we move from the lab to the stars. Pillar 5. This one's a doozy. This is the Miller limit and the quantum packing fraction. Ladies and gentlemen, we're introducing a brand new metric to material science, the quantum packing fraction, V sub Q. Sorry, my voice. Think of our ZPF array as a cage for an electron. If you design that cage to be 100 times larger than the electron's ground state, you create a potential for expansion. For a century, physics has asked one desperate question: how do we make quantum effects happen at room temperature? The world answered with liquid nitrogen and billion-dollar cryostats to expand the de Broglie wavelength. We propose a different way. It is not about freezing matter. It's about quantum packing. The technical definition. In classical material science, we characterize a lattice by how it arranges atoms, the atomic packing factor. But in the era of vacuum engineering, that metric is incomplete. Our ZPF array relies on the quantum packing fraction V sub Q. Here you see the equation. On the screen, you see our mathematical trigger, the quantum packing fraction. We defined phi sub Q as the dimensionless ratio of the electron wave packet's spatial expansion, the effective de Broglie wavelength, relative to its confinement volume within the Wigner-Seitz cell. Mathematically, it is the cube root of our 100-to-1 volumetric asymmetry, which brings us to our critical design threshold of 4.64. In the equation, you have V sub wave packet equals the effective electron wave function volume, and V sub WS equals a Wigner-Seitz cell volume. The trigger, the 4.64 ZPF array specific Miller limit. By engineering a deliberate 100-to-1 volumetric asymmetry, we modify the quantum phase space accessible to the electronic wave function. When phi sub Q is approximately equal to 4.64, the cube root of our 100-to-1 asymmetry, the effective de Broglie wavelength expands to the Wigner-Seitz boundary. This enables intersite overlap, a Mott transition applied to hardware. Yes, a Mott transition applied to hardware. At this threshold, electronic states become delocalized across neighboring lattice sites, forming a delocalized Madelung wave cloud. This is macroscopic quantum coherence at room temperature. Note, 4.64 is not a universal number. The logic here is universal. Coherence occurs when the linear expansion saturates the lattice. 4.64 is the specific sovereign frequency of ZPF technologies array. We've engineered our 100-to-1 geometric asymmetry specifically to trigger the MQC transition at this precise threshold, allowing us to hydroplane on the quantum vacuum without fracturing the metric. We have three emergent hypotheses. At the 4.64 Miller limit, the entire cavity array behaves as a single coherent superfluid interface, triggering three world-changing effects. One, metric softening, modification of the vacuum boundaries conditions, and effective electromagnetic impedance analogous to phase transitions and superfluidity. The array ceases to fight the vacuum and begins to surf it. Two, Coulomb screening, enhanced screening potential due to delocalized charge density. Theorized to facilitate lattice-based interaction and enhanced probability of lattice-mediated nuclear interactions, ambient temperature alpha spikes. And three, geometric coupling, geometry-driven intersite coupling, forcing electronic coherence analogous to Mach transition-induced phases, serving as a room temperature function equivalent to Cooper pairing. The scientific pivot here, Sir Neville Mott won a Nobel Prize for proving that if you force electrons to become big enough, material properties change instantly. We've taken Mott's vision and turned it into hardware. We aren't fighting the vacuum with brute force. We're tuning matter into harmony with the real ZPF plenum itself. The aha moment here is this. One, geometric condensation. We use our 100-to-1 cavity geometry to condense the ZPF flux. And two, quantum synchronization. We hit the 4.64 Miller limit to synchronize with that condensate, achieving an inviscid superfluid state where the lattice and the plenum move in total harmony. Pillar 6, the recursive Miller saturation threshold, which we kind of already covered. Earlier, we discussed the theoretical foundation of the recursive Miller saturation threshold. Now let's look about the engineering payoff. In Pillar 5, the Miller limit is the boiling point. Pillar 6 is the steam engine. Once we reach 4.64, the vacuum ceases to be a rigid barrier and becomes an elastic medium. We aren't hitting a ceiling. We're opening a recursive doorway. Under the Setterfield and HRP frameworks, we enter a self-reinforcing feedback loop. The ZPF surge raises local Planck's constant, the graininess of the plenum. The expanded electron wave packets increase the vacuum's energy holding capacity, and the system suddenly accommodates higher densities without dielectric fracture. It's a self-stabilizing ascent. The more the metric softens, the more resonance it can sustain. There's three stages of this transition. We can visualize this journey in three regimes. Stage 1, the resistive regime below 4.64. The vacuum is stiff. Every unit of momentum is earned against high impedance inertial drag. Stage 2, the transition threshold at 4.64, the knee of the curve. Resistance begins to dissolve and the local refractive index, K sub m, accelerates. Stage 3, the superfluid regime above 4.64. We're now hydroplaning on our own wave wake. Motion generates a metric surge. The surge increases Planck's constant, and higher Planck's constant further masks the drag of the background plenum. The result is what we call the sovereign system, a self-contained metric soft bubble that is effectively decoupled from the standard inertial drag of the universe. At this moment, our array is no longer translating force against the vacuum. We're transducing the vacuum's own latent energy into directed flux. The vacuum has become the reaction mass, delivering the full refractive index and the 15 millinewtons baseline thrust that we have engineered. Yes, 15 millinewtons is what we're hoping to accomplish. Why hydrodynamics? Because the vacuum is not empty. In SED, it's a dense reactive plenum. When we modulate it at scales of our array, collective behavior takes over. like a crowded concert floor that suddenly moves like a liquid. We're not pushing against the void, we're plumbing the plenum. Madelung gives us the fuel, Bohm gives us the rails, and Lorentz gives us the grip. Without all three, all you have is entropy. With all three, you have a solid state, quantum hydrodynamic engine. The vacuum is not literally a liquid, but it behaves like one at high mode density. Metric suction is our shorthand for the asymmetric Lorentz back reaction and Madelung pressure gradients we create. Conclusion of the 6 pillars. By reaching the dimensionless 4.64 Miller limit and entering the recursive regime, we emulate the extreme nonlinear effects of the Schwinger limit, but at approximately 7 orders of magnitude lower potential gradient or field strength. Instead of needing petawatt lasers or high temperature plasmas, our array is designed to achieve the same kind of vacuum polarization and pair back reaction via the nonlinear multiplier to refractive index simply by resonating the real ZPF at room temperature. At that moment, the lattice should become a coherent Madelung wave cloud, a room temperature macroscopic Bose-Einstein condensate. The lattice walls will turn into a perfect superfluid interface with the plenum. The Coulomb barrier will become geometrically transparent, and we should see 8.7 MeV alpha spikes from the vacuum-catalyzed anetronic fusion, all as byproducts of the same coherent state. Now, I had a little simulation worked on here, or worked up here. You can call it the fifth state of matter if you want. Maybe you don't like that. It's the Madelung wave cloud transition. In the metric soft regime, individual fermionic identity dissolves as electron wave packets bridge their Wigner-Seitz cells. This unified wave cloud acts as a single quantum fluid, enabling propellantless suction and zero resistance conduction. What you're seeing is the direct coupling between peak power input and the physical expansion of the de Broglie wavelength through the proxy of the ZPF energy density. So here you can see on the right, we got the one resisting lattice state, one being the relative Planck's constant, 3 wave packet dilation, 4.64 the Miller limit, 6 the superfluid regime. At 0 watts power, which is the classical state, you can see that the electrons are in their ground state confinement. The wave packet is a tiny dot in the center of a massive 100 unit Wigner-Seitz cell. Quantum packing fraction is near 0. At this stage, matter is cold, localized, and particulates. At 2 watts power, you have the inflationary phase. We start the actuation of the cavities and notice the packets beginning to breathe. At 2 watts, we've increased the local ZPF density enough to grow the electron by about 1.5x its original diameter. It's still a particle, but the fuzziness, the quantum uncertainty is increasing. At 5 watts, we're approaching the Miller limits. Expansion is accelerating. The electron is now 3 times its original size. It is starting to fill the walls of the atomic lattice. The impedance of the array is starting to jitter as we enter the three-threshold regime. At 8.6 watts, we reach the 4.64 Miller limit. The surge in local Planck constant stretches the electron's Compton volume until it hits the Miller limit, the point of geometric saturation. The linear expansion has reached the cube root of our 100-to-1 volumetric asymmetry, exactly 4.64. The so-called bird has filled its cage entirely. This is the knee of the curve where the physics begins to latch and thrust becomes nonlinear. At 10 watts, we have the phase transition and total overflow. The wave packets are no longer individual circles. They've merged into a single continuous Madelung wave cloud. The grid lines of the Wigner-Seitz cells have vanished. Individual atomic identity is gone. We've achieved macroscopic quantum coherence at room temperature. This is the recursive saturation threshold of pillar 6. What you're seeing in the sim is hardware phase change. It's the lattice opening up to the vacuum, but the real thrust comes from what the sim does not show, the back reaction of the vacuum plenum itself. As our cavities dynamically actuate, we're jittering the particle-antiparticle pairs of the ZPEC at Compton scales. We're effectively thickening the vacuum until it becomes a reactive superfluid along a very steep Madelung pressure gradient. This creates a high ZPF density zone behind the array and a low density depletion zone ahead of the array. The thrust is metric suction. The array lattice is drawn into the thinned vacuum. In the simulation, we model a growth rate of approximately 0.4 to 0.5 linear expansion units per watt. And to be clear, we're talking about peak resonant loading, not continuous thermal load. By utilizing sub-microsecond pulsing, we hope to achieve the energy density of the 4.64 Miller limit instantaneously. This allows us to exploit the staircase effect, where the vacuum's local refractive index remains elevated between pulses while maintaining a low average power load that preserves the structural integrity of the array. Crucially, this pulsing frequency allows for a metric flush, a periodic reset, where the local speed of light returns to C sub 0, preventing the slow light trap from bottlenecking heat within the lattice walls. We're effectively outrunning the thermal limit to capture the metric gain. Some final notes here. Please bear in mind HC invariance, a surge in Planck's constant, and the drop in C is invariant. The product HC remains constant. This explains why atoms don't fly apart as the metric softens and maintains the stability of the fine structure constant. I'd like to reiterate that propellantless suction means creating a metric pressure gradient. We're thickening the vacuum behind the wave packets, the dense backstop, while the front remains soft, effectively shielding the ray from inertial drag. One last thing here, connecting the engineering with cosmology. Primordial resonance emulating the day 4 pinch. To truly grasp why a mere 10 watts can trigger such a violent phase change in our array, we must look back to the history of the universe itself. According to Setterfield, our cosmos has already undergone the exact transition we are attempting to recreate in our array. In the earliest epoch, day 1 of the universe, the 0-point field density was remarkably low. The vacuum was thin. The speed of light was very high, almost instantaneous, and Planck's constant was low. Stable atomic matter could not yet form. Vast filaments of plasma expanded across the void without the stochastic jitter needed to pinch them into stars and galaxies. But on day 4, the ZPF density reached a critical threshold. As the vacuum thickened, Planck's constant surged, speed of light slowed, preserving HC invariance that keeps matter stable. And this increase in local vacuum resistance provided the physical pinch that compressed those filaments. As you know, plasma filaments are already unstable, into the first stable nuclear fires. Stars were born, galaxies were born, not through a change in temperature, but through a change in the constants of the metric itself. Our ZPF array is designed to perform a local day 4 emulation. We're not reaching for the absolute density of the primordial past. That would be impossible. We're reaching for the same geometric saturation point, the Miller limit, at phi sub q equals 4.64. By pumping the local ZPF density within our proprietary cavities, we force a local surge in Planck's constant. When we hit 10 watts, we're not just heating up the lattice. We're creating the exact pinch conditions where the Coulomb barrier becomes geometrically transparent and the vacuum itself begins to catalyze the reaction. So when we prototype this and we see those 8.7 MeV alpha spikes on our monitors, we are not seeing a nuclear byproduct. We're seeing the signature of a vacuum that has been reauthored. We're using 10 watts of resonance to awaken the same primordial forces that ignited the sun. This is not just propulsion. This is the liberation of energy from the plenum's breath. The Miller framework transforms SED into actionable metric engineering. ZPF Technologies is boldly leading this transition from QED to SED, from mathematical ghost to a real physical plenum. All that is possible remains to be accomplished. Jules Verne. For a century, QED confined the vacuum to abstract fluctuations and renormalization. SED restores it as a tangible, dynamic continuum ripe for modulation. By engineering local ZPF density gradients within our array, we will hope to achieve what once was unthinkable, that directed asymmetries in the Lorentz sea for propellantless propulsion, vacuum-catalyzed reactions that soften Coulomb barriers for clean aneutronic fusion, and tunable local metric effects that could redefine energy in transit, all in a flat Minkowski space without exotic matter or extra dimensions. This is no longer an academic debate. It's a new and existential engineering race to the future. And we stand as the vanguard, committed to rigorous R&D and ethical deployment. The vacuum is not an empty void. It's a vibrant sea awaiting resonance, and SED equips us to finally conduct its symphony. If you're interested in more information on ZPE, this book right here is my main primary source. This is Barry Setterfield's book. This man is 80 years old. He was offered 2 honorary PhDs for his life's work in this book. Talks all about the ZPE, as well as a lot of cool stuff about the implications of the ZPE back when it was lower in Earth's history, including things like gigantism in the fossil record. A lot of cool stuff in there. You can get it from their website, but they're 80 years old and they maintain it themselves. And when I tried to get a recent copy, it never shipped. And I called the number on the receipt, and it was his wife, Helen, that picked up the phone. And I said, "Hey, Helen, I've been corresponding with Barry over the years." She turns around and she says, "Hey, Barry, it's Doug Miller." And she said, "Well, he'll try to get it out to you soon. It'll probably be next week because he's got to put a battery in his car." So they're doing all this themselves, maintaining their website and sending out material. But they do say on their website that if you want a copy of this book for free, they can send it to you via email PDF instead. So thank you, Barry Setterfield, for all your work that I've been able to learn from and glean from and to share with this APEC audience. Thank you, Tim. That concludes my presentation.